Okay, notes 3.1, exponential functions. So up until now, we've covered algebraic functions, things like quadratics, cubics, quartics, but now we're going to talk about exponential functions, and they are a little bit different. We're now going to refer to exponential functions as transcendental functions. We don't use that term a whole lot, but they are different from the typical algebraic functions. So we're going to compare the two. First of all, passing the vertical line test. So any function is going to pass the vertical line test. So we know that those are algebraic and also transcendental functions or exponential functions will pass them as well. With algebraic functions, when we want to solve or graph, or I should just say solve, we obtain values through our basic operations, adding, subtracting, multiplying, and dividing. So through those operations, we can solve all of our algebraic functions. Transcendental functions actually go beyond algebra. None of those operations sometimes will work to solve for the variable that we need. So it's beyond algebra, and what we're going to see happen in this chapter, as you have before in Algebra 2, is that we're going to have logs that we can use and the tools that logs provide to solve these equations. Okay, so an example of an algebraic would be y equals x to the third, your parent function for a cubic. But a transcendental function, an exponential, would be y equals 3 to the x, where the variable is actually your exponent. Okay, so now we're going to take a look at some parent functions for exponentials, and we're going to just sketch the graph and analyze them. Again, we're going to talk about some of the characteristics, domain, range, intercepts, asymptotes, and behavior, and where the function is increasing or decreasing. So if you remember from Algebra 2, your parent function for an exponential was b to the x. However, when we have no numbers in there, we typically will use something like 3 to the x or 2 to the x as our parent function. So in the first one, in example A, we're going to use 3 to the x. So we're going to make a chart, and we're going to plug in some values for x. Let's do 0, 1, 2, and we'll throw in a negative. So as we plug those in for x, 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, and 3 to the negative 1, if you remember, is going to be 1/3. It won't make the function negative, but it puts that power down into the denominator. So let's graph this now to see what this exponential looks like and kind of be reminded of the parent function. There's 0, 1, there's 1, 3, 2, 9 is all the way up here, and then negative 1, 1/3. So negative 1, 1/3 is right there. So as we look at this exponential, we have growth. One of the key things with exponential functions, you may remember, they all go through the point 0, 1. Because anything raised to the 0 power will be 1. All right, so as we look at this graph now and we look at the characteristics, our domain will be everything from negative infinity to infinity. Our range will always be positive, so from 0 to infinity. Then we have our x and y intercepts to look at. As far as an x-intercept, there isn't one. We're never going to get 3 to the x to have a value of 0. But as far as our y-intercept, when x is 0, we know that's always 1. So we have 0, 1 for the y-intercept. The vertical asymptote, there isn't one. There's nothing that would make this function undefined since we can plug in any domain value we want. The horizontal asymptote, if you look at this behavior, we have a horizontal asymptote at y equals 0. It's going to get very, very close to 0 and never approach it. As we talk about end behavior, we're going to look at the limit as x approaches positive infinity, f of x will go to positive infinity as well, and the limit as x goes to negative infinity of f of x will go to 0. We're also going to talk about, I think it was, asymptotes and behavior, and whether or not the function is increasing and decreasing. So as we ride this graph from left to right, it is increasing from negative infinity to positive infinity. Okay, so that's 3 to the x and those characteristics. Now we're going to look at b, 2 to the negative x. So how does this change when the variable is negative? Well, what we just saw when we did 3 to the negative 1, we were reminded that it gets put into the denominator. So if we write this function, f of x, that's actually 1 over 2 to the x power. So let's plug in some values here and see what we have as a graph. So x, y, again I'm going to plug in 0. We'll plug in 1, maybe 2. How about negative 1 and negative 2? And let's see what we have. So how does having a negative exponent change this exponential? So when I plug in 0, 1 over 2 to the 0 is 1. 1 over 2 to the first will be 1/2. 1 over 2 squared is 1/4. 1 over 2 to the negative 1, well, 2 to the negative 1 is actually going to be, or 1 over 2 to the negative 1 is actually going to be 2. It's going to bring that value up into the numerator as 2 to the positive 1. And 1 over 2 to the negative 2 will become 2 to the positive 2, which is 4. Okay, so let's graph these now. I have 0, 1, 1, 1/2. I have 2, 1/4, even smaller, negative 1, 2, and 2, 4. So as you can see from this, we have exponential decay. So as we look at these again, remember this is growth, and this represents decay. All right, now let's go talk about the characteristics for this second one in B. Our domain, once again, is negative infinity to infinity. Our range, still, we will not get any negative numbers, so it's 0 to infinity. Our x-intercept, there is not one. There's nothing that we could ever plug in to get 0 again. Our y-intercept is still 0, 1. Vertical asymptote, there is not one. Nothing will make it undefined. Horizontal asymptote is still y equals 0, or the x-axis. As we look at this limit, as x approaches infinity of f of x, it is 0. And the limit as x approaches negative infinity of f of x is infinity. And then last but not least, this is decreasing over the entire function, so from negative infinity to infinity. So there are a couple parent functions and their characteristics. Okay, now we're going to basically do the same thing, so it will be a little redundant, but just reinforcing these characteristics and the graphs that they go with. So we're going to look at these again, exponential growth and exponential decay, only this time we really don't have any numbers plugged in, like the 2 or the 3 is the base. So we have these two graphs, this of course being growth, but look closely at what this says. Exponential growth as long as the base is greater than 1. So these would be equations like 7 to the x, 3 to the x, 4 to the x. So those would all be representative of growth. And then we look at the decay, and this is where b, your base, is a fraction. It's greater than 0 and at the same time less than 1. So this may be something like 1/2 to the x power, 2/3 to the x power, so on and so forth. So once again, let's go ahead and look at these characteristics. First, we'll talk about growth. So for exponential growth, the domain is negative infinity to infinity. The range is the range is 0 to infinity. The x-intercept There is not one. The y-intercept is 0, 1. Continuity, yes, absolutely continuous. Symmetry, there is no symmetry. Extrema, in other words, relative or absolute maximums and minimums, there are none of those. Decreasing, it never decreases, so that doesn't apply. Increasing, always, from negative infinity to infinity. And end behavior, as x goes to infinity, f of x goes to infinity. And as x goes to negative infinity, f of x will go to 0. Okay, and then we're going to look at exponential decay. Once again, the domain is negative infinity to infinity. The range is 0 to infinity. There is no x-intercept. The y-intercept is 0, 1. Yes, it's continuous. No, it doesn't have symmetry. No, it does not have extrema. It is decreasing everywhere from negative infinity to infinity. And it's never increasing, so that doesn't apply. And end behavior. As x goes to infinity, f of x will go to 0. And as x goes to negative infinity, f of x will go to positive infinity. Okay, so now that we've talked about the characteristics of those parent functions a couple of times, let's apply some of the techniques that we've done with previous types of graphs and their transformations and use them to apply to these exponentials. So we're going to use the same techniques to transform these transcendental functions that we've used before. For example, a k value or something that you add to the whole function is going to move it up and down. Something that is added or subtracted directly to x is going to move it left and right. Making the whole function negative, we'll flip it over the x-axis. Adding a factor in front of the base will, of course, stretch it or compress it vertically. So same things. Let's look at the first one. We're going to use the graph of 2 to the x right here to describe the transformation that results in each function. Then we're going to sketch them. So 2 to the x, if I just look at 2 to the x and I make a little chart of what's going to happen, I know that if I plug in 0, I get 1, 1, I get 2, 2, I get 4, and negative 1, I get 1/2. So these are the ordered pairs for that parent function. And let's see how they transform with each of these. So if I have g of x equaling 2 to the x plus 1, we're directly doing something to the x. That's going to be a horizontal shift. So this is going to move 1 unit to the left. It looks like it's going to be right because it's plus, but that's minus a negative, so we're going to move this 1 unit left. And that's all that this does. So what we're going to do, I'm going to come down here, make a new little chart, and see what those points are now going to do. So if I move 1 left, that only affects the x values. So my y's are going to stay the same. 1, 2, 4, 1/2. However, my x values, if I want to go left, I'm going to have to subtract 1. So 0 goes to negative 1, 1 goes to 0, 2 goes to 1, and negative 1 goes to negative 2. Okay, so if I graph my parent function, and I'm going to just do that with a dotted line, I have 0, 1, 1, 2, 2, 4, negative 1, 1/2. So this is the parent function, 2 to the x. And now if we transform this by moving it 1 to the left, I have negative 1, 1. I have 0, 2, 1, 4, and negative 2, 1/2. So this is the function that we now have, just moves 1 to the left. Okay, let's look at b. H of x is 2 to the negative x. So with the negative x, when I make the x from positive to negative or negative to positive, this is going to reflect over the y-axis. So as I reflect over the y-axis, I know that my ordered pairs are going to change. So The part that will change will not be the x's. It will be the x's. So I'm going to go from 0 to 0, 1 to -1, 2 to -2, and -1 to +1. And then my y's will stay the same. 1, 2, 4, 1/2. So we know now what the parent function looks like. It's over there in example A in purple. So let's graph this new one, reflecting over the y-axis. 0, 1 still. I have -1, 2, -2, 4, and 1, 1/2. So this now looks like exponential decay. Even though b is greater than 1, when we reflect it over the y-axis, it's going to look like decay. Okay, letter C, we have -3 times 2 to the x. This is not -6 to the x. Absolutely not. So we have to keep those separate. Order of operations tells me that 2 to the x, you'd have to do the exponent first before you multiply and divide. So when we look at the graph of 2 to the x and we have those ordered pairs, what kind of transformation will happen? So we know that the negative is going to reflect it over the x-axis. It's making the whole function negative, so this reflects over the x-axis. And the 3 is a vertical stretch by 3. Okay, so when we have to consider what we're going to do first, if we're going to reflect or stretch or shift, actually these two are going to go together. So the only thing that's going to change will be my y values, and I'm going to multiply them by a -3. So as I look and make a new chart from my parent function, my x's will stay the same, 0, 1, 2, -1, but my y's are now going to be -3, -6, -12, which will be off of our graph, and, sorry, I lost my train of thought, and 1/2 times -3 is going to be -1.5 or -3/2. So as we look at this, 0, -3, 1, -6, and then I have 2, -12, that's going to be way down here, and then I have -1, -1.5. So I actually have this vertical stretch of 3 and also reflecting over the x-axis. Okay, so that takes us through a few transformations. Okay, so now we're going to look at, we're going to start to look at the bases in particular. So we like it when we have bases of 2 or 10. Those are pretty easy to work with. However, the majority of real-world applications rarely use bases 2 and base 10. They actually use this number e. Sorry, you can't really see it with the highlight or with the marker there. So 2 or 10, the number e. This value is actually called the natural base, and you may remember that natural logs are in base e. So you don't need to memorize this next piece right here, but this, just interesting, this is where that value comes from. The number e is actually the limit as x approaches infinity of this function, 1 plus 1 over x, all to the x power. So as you might remember, e is not a variable. It has a value. As the value e gets closer and closer, as x gets very, very big, this value gets very close to 2.718. That is the value of e. So the function that is given by f of x equaling e to the x, this is called the natural base exponential function. It has the same properties as all of the other ones that we've talked about. Okay, so in that, we're going to graph a few transformations of this. Once again, this is still going to go through the point 0, 1, but we're just going to make some sketches as to how these are affected. So with this one right here, to describe the transformation that results from e to the 4x, the 4 is going to be a horizontal compression by a factor of 4. This is going to make it get very, very narrow, a little bit faster. So again, these still go through 0, 1, and it's going to grow even faster than just e to the x. Okay. Then in the next one, we have e to the negative x plus 3. So the first thing I see is that it's going to go 3 units up, and the negative to the x is going to reflect it over the y-axis. So reflect over y. Okay, so whereas I used to have the point 0, 1, if I move up 3, I now have 0, 4 right there. Where I used to have a horizontal asymptote of 0, this now is going to have a horizontal asymptote of 3. So, oh, and it reflects, forgot about that part. So now as we reflect over the y-axis, we're going to have a graph that looks similar to this. And again, these are just sketches getting an idea of what they do with certain transformations. The last one, c of x is equal to 1/2 e to the x. So the 1/2 is going to be a vertical compression. It's going to make e to the x a little bit wider. So vertical compression by a factor of 1/2. It will still go through 0, 1, but this will be a little bit wider than maybe the parent function. Okay, so that takes us through those. Now we're going to do some application. So these should be pretty familiar to you. You've done these before, maybe as early as middle school, not knowing that they were specifically exponential functions, but they were, and they fit really well into this section. So, okay, so compound interest. A of t equals p times 1 plus r over n, all to the nt power. So this is an equation that we're going to use when we're talking about money, talking about finances, and we're going to compound or apply the interest different amounts of time throughout the year. So as we look at this, p is going to be our principal. The r will represent the interest rate we have, and we have to put it in decimal form. Compounded n times per year. You may remember n would be 12 if it was compounded monthly. N would be 52 if it was compounded weekly. N may be 4 when it was compounded quarterly, so on and so forth. So it's however many times you're dividing up that interest and applying bits and pieces of it throughout the year. And then t in this equation is, or in this algorithm, is always in years. Then you have continuously compounded interest. The key word here is continuously, and you will see that in the problem. Continuously compounded interest. And a lot of times we refer to this as the PERT formula because that's literally what it spells. And all of the variables mean the same thing. A is your resulting amount, P is your principal, E, again, is not a variable. That's my 2.718 always. And then to the RT power, rate and time again. So those are going to be very familiar to you guys. I want to point out that these top two equations in the gray box, these are money equations. You're going to use those when you're talking about money and investments. So then we're going to go to a couple others that you have, exponential growth and decay. These, and then you have continuous exponential growth or decay. These are talking more about things like growth and decay of a population. Maybe the value of a car depreciating, even though that is money. We have a way to show decay with that. Continuous exponential growth or decay. Things like half-lives, of substances or the rate of bacteria growth. So these maybe are thought of to be more in the sciencey realm when we use these. Notice as we look at exponential growth or decay, let's go through this formula. It says that n, which is the resulting amount, equals n sub 0, and down here that tells us that n is the initial quantity, the amount we start with. Then it's 1 plus r, which is my rate. It's either growth or decay. Okay, r can be either one, and then it's raised to the t power. And with this, t can be any given amount of time. Okay? So then, if r is a growth rate, we're going to have a positive value. If it's a decay rate, then r will have a negative value, which should make sense. The continuous function for growth or decay, the continuous exponential growth or decay function, this is very, very similar to PERT, almost identical. It just has different variables. N sub 0 is the same as the p value. K is the same as the r value. K represents growth rate or decay, so it's growth if it's positive, and if it's decay, that's when it's negative. Okay, so we're going to finish up this section by just doing some applications with these formulas. Example 4 says Mrs. James invested $300 into an educational account for her daughter when she was an infant. The account had 6% interest rate. If Mrs. James does not make any other deposits or withdrawals, what will the account balance be after 20 years if the interest is compounded semi-annually, monthly, or daily? So that right there, a lot of clues to let me know that this is going to use the compound interest formula right here. N is the number of times it's compounded, so we can actually go down through here. Semi-annually will be twice a year. Monthly, N will be 12 times a year, and daily, N will be 365. So, if we look at semi-annually, we've got $300, that's the principal. The 6% interest rate, we're going to use 0.06 when we calculate with R. And then we want 20 years, so that's our t value. So if we plug this all in, we get our amount to equal 300 times 1 plus R, which is 0.06, divided by 2, and then raised to the 20th power. When you go to your calculator, be very careful as you enter these in. I like to work from the inside out. If you kind of watch as I highlight, I would do the 0.06 divided by 2. I would hit enter. Then I would add 1, hit enter. Then I'd raise that to the 20th power. How about I forgot 2 times 20? Pause. N times t, so 2 times 20. So I would then raise it to the 40th power. And then after all that, I would multiply everything by 300. So when you put that into the calculator to the nearest cent, after 20 years, she would have $978.61. So I would encourage you to stop this video, go through, and do these next couple of problems yourself, then turn it back on and see if you got the right answer. Okay, now we're going to look at monthly. So A will equal 300 initial, 1 plus 6% divided by 12, raised to the 12 times 20 power, and that amount will give us $993.06. Then if we're going to do this daily, our amount will be 300 times 1 plus 0.06 divided by 365, and then it will be raised to the 365 times 20 power, and that amount gives me $995.94. So there are each of our balances, 978, 993, and 995. They get a little bit bigger, but not a huge significant difference. Okay, looking at example number 5, we almost have the exact same problem, only we see a little bit of a change. Mrs. James found an account that will pay 6% interest compounded continuously on $300. What will be the account balance after 20 years? Okay, so we're changing this up a little bit. This is going to be the PERT formula, principal times e to the RT power. So the amount is equal to 300 initially, e raised to the RT, which is 0.06, times 20. When you go to your calculator and plug that in, you should get $996.04. Not much difference, but it is slightly better by less than $1 with the daily. Okay, let's look at example 6. Mexico has a population of approximately 110 million people. If the population continues to grow at the described rate, predict the population of Mexico in 10 and 20 years. Okay, so we have a growth rate of 1.42%. So we're going to first look at 10 years. So this formula is what we're going to use, the growth formula, n equaling n sub 0 times 1 plus r to the t power. Okay, so I have n equal to an initial amount of 110 million, 1 plus 1.42% as a decimal is 0.0142 raised to the 10th power. So that amount should be 126,656,869. Now keep in mind, when you do this in your calculator, you're going to see a decimal after 126, but that is in millions. So the rest of those numbers after the decimal place are all going to come into play here as we move that decimal point 6 places to the right. So let's look then at 20 years. So basically the same equation. You could actually just hit second entry in your calculator and just adjust the variable or the exponent to 20. So 110 times 1 plus 0.0142 to the 20th power. And that population will be 145,836,022. Okay, so that is annually, a growth rate for population annually, not talking about money. Now we have population in the next one growing continuously. So after 10 years, continuous growth is going to be this formula, n equaling n sub 0 e to the kt, just like the PERT formula, n sub 0, only with some different variables. So for 10, we would have the resulting amount equals 110 e to the 0.06 times 10 power, and our population after 10 years would be 126,783,431. Then I'm going to look at 20 years later, so t equaling 20, I have n equaling 110 e to the 0.06 times 20, and that population is 146,127,622. 127,622. And there are your populations. Okay, last question on these notes, example 7. So now we're going to take our data from a little different venue. We have a table that we're going to have to interpret. It says the table shows the number of recorded cases of chickenpox in the United States in 1980 and 2005. So A says if the number of cases is decreasing at an exponential rate, identify the rate of decline and then write an exponential equation to model this situation. So this is exponential decay. We're not talking about money. So here's our algorithm. N equals n sub 0 times 1 plus r to the t power. Okay, So as we try to look at this table and talk about some variables, we actually know that we're going to need to look for the rate of decline. That's R. So R is the first thing we don't know. Let's see if we can plug in all the other things. N, the resulting amount, that is actually the 32.2. That's our resulting amount, which makes N sub 0, our initial amount, the 190.9. And this is in thousands. So we're going to use 32.2 as the result. The initial was 190.9. And then 1 plus the rate that we don't know. And then the time, T. If we look, from 1980 to 2005 is 25 years. So now we have everything we need to solve. And we're going to begin by dividing both sides by 190.9. I don't want to go to my calculator too soon and lose accuracy, so I'm going to leave it at that. And guys, I'm going to carry my work down here. So now I have 32.2 divided by 190.9, and that's equal to 1 plus r to the 25th. So if I want to get to r, I am going to have to take the 25th root. That's right, 25th root of both sides. And then I'll have 1 plus r equaling the 25th root of 32.2 divided by 190.9. And to solve for r, we're going to subtract 1 from both sides. I can put negative 1 plus, but I'm going to rewrite this because I know that's probably not real fun to look at. So the rate is the 25th root of 32.2 divided by 190.9 minus 1. When you go to your calculators, you are going to get a decimal value of negative 0.069 for your rate, approximately. And it does make sense that it should be negative. So that's the first question, the rate, negative 0.016. No, there's no 1, is there? Yeah, no 1. Let's see. Negative 0.069. But then they want to know the equation. Now that we have the rate, what would the equation be? So we can plug the things in that we know that will not change according to this data. So n is equal to n sub 0. That's not going to change. The initial is the initial. And then 1 plus a negative or minus 0.069 to the t power. And we can leave that right there as our model. And we have our rate. Okay, in part B it says use the model to predict when the number of cases will drop below 20,000. So at this time we don't have any logarithmic tools to use. So we're actually, what I did was looked at a graph. I graphed this. So we have this exponential decay, and then I put that into y1, this model, and then in y2 I put my 20,000. Actually, I probably should put it a little lower. There's my 20,000. So this was in y2. And I just put 20 because we already know we're in thousands. So then I looked at where they intersected, and that told me the point where it was about 20,000, and that ended up to be about 31.5. So x was about 31.5, which means in about 32 years, the number of cases will drop below 20,000. Okay, so that takes us through these notes of exponential functions.